Visible light, an introduction. It's radiant energy that can be detected by our eyes. We use the word luminous for things that emit light, like the sun and the light bulb. Other objects merely reflect light. They need to be illuminated. The pinhole camera creates an inverted image because the light rays travel in a straight line. So the only place that flame could be seen inside the box is over there. The very first cameras were just a box with a hole in it and some photographic paper at the back, which was sensitive to light. So we represent the light rays as arrows. Objects are either transparent, like the windows, or translucent, like the frosted glass over here. It diffuses the light, so you don't get sharp images coming through. And then, of course, the word opaque means nothing passes through, so light doesn't go through the walls or the frames or the floor. Shadows. The further the object is from the wall, the bigger the shadow. And the closer it goes, the smaller the shadow. Speed of light. Well, speed of light is very, very fast. 3 times 10 to the 8 meters per second. In terms of kilometers, it's 300,000 kilometers per second. So if light could travel around corners, it would go 10 times round the Earth in 1 second. Speed is distance over time, and if we put it in a triangle with distance on top, we can see that if we cover this with your finger, speed is equal to distance over time. But distance, cover that with your finger, is equal to speed times time. If it takes 8 minutes for light to reach us from the sun, how far away is it? Well, distance is speed times time. So we take this in kilometers, and it's 8 minutes, so we multiply it by 8 times 60 seconds per minute, and we end off with 144 million kilometers. That's how far the sun is away from us. The space shuttle travels at 30,000 kilometers per hour. How long would it take to travel the distance to the sun? Obviously, it can't go to the sun, it would just burn up. So now we want to find time. Go back to this arrangement, put your finger on time. What's left? Distance divided by speed. So we take the distance divided by the speed, and we end up with 4,800 hours, which is 200 days. Astronomical distances are so far that we measure them in light years. So calculate how far light travels in 1 year. This is called a light year. Distance, again, is speed times time. So we've got so many kilometers per second, times 60 seconds in a minute, times 60 minutes in an hour, times 24 hours in a day, times 365 days. And we get this enormous number, which if we round off to 10, then we get 10 trillion kilometers. 10 with 12 zeros behind it. The nearest star to Earth is 4 light years away. So calculate how far that is in kilometers and how long it would take the space shuttle to travel that distance at that speed. Well, we've already figured out that 1 light year is so far almost 10 trillion kilometers, and therefore if we multiply it by 4, we're about 40 trillion kilometers away to Alpha Centauri. Now, they've recently discovered a solar system around this constellation, and if we work out how long it would take to get there, well, time is distance divided by speed, so we take that distance we've just calculated divided by the speed of the space shuttle, and if we divide that number of hours by 24 hours in a day, we end up with so many days. And if we divide it by 365 days, we end up with 144,000 years to travel in the space shuttle, the fastest vehicle humans have ever made. It would take 144,000 years to get there. So we're going nowhere. We better look after this place. What else can light do? Well, we can have a refraction of light. White light comes through a prism and it breaks up into its colors. We'll see this with some equipment a little bit later. And these colors, red, orange, yellow, green, blue, indigo, violet, are the colors of the rainbow. This side of the spectrum has the longer waves. This has a slightly lower frequency, and these have the higher frequencies. So if we depict it by a wave action like this, the shorter wavelengths are on the blue side, the violet side of the spectrum, and the longer wavelengths on the red side. And the red rays are refracted or bent the least, so that is why it splits white light up, causes the spectral colors. Here we have a beautiful double rainbow, and here's one taken recently in Southend from my backyard. There's Fort Frederick as a landmark. Isn't that beautiful? So how do rainbows form? Well, all the raindrops have light coming in, and there's a bit of bending, changing direction, and a bit of dispersion occurring. Then it reflects off the inside of the drop and comes out even more refracted and separated, thus giving us the colors. And this angle is 42 degrees. The visible light is only part, if this all fits into there, it's only part of a much bigger spectrum. Part of the electromagnetic spectrum, which ranges on the high frequency side from gamma rays all the way down to the low frequency side of radio waves. So radio waves, microwaves, TV waves are somewhere in between. Infrared rays, this is heat, and then we get ultraviolet. All of these are dangerous. Ultraviolet burns your skin, you get sunburnt. X-rays, and finally gamma rays, which come from radioactive substances, extremely dangerous. Properties of light. Well, light can bend when it passes through a transparent medium. Like here, the glass of water is acting as a lens, and thus magnifying what we're seeing behind. And here it appears as if the straw is broken. Light can bounce, reflecting off surfaces. In fact, everything you're seeing now is because of reflected light. And finally, light can be absorbed. So if we have a green thing, it absorbs most of the colors of the rainbow, except for green, which is reflected into your eye. The human eye contains a lens. Both the cornea and the lens start bending the light, refracting the light, and any illuminated object or object reflecting light will form an image on the back of the eyeball, the retina, and there are light-sensitive cells there which detect the light and pass the signal via the optic nerve to your brain. If we want to make a drawing, we encourage you to learn how to make simple schematic drawings. Then a drawing needn't be any more complex than this. The iris, that's this part, controls the amount of light that comes in. So let's look at another drawing of that. If the light increases suddenly, then the iris contracts. Watch here. We see how the iris contracts, letting less light in. And we're familiar with, when we go out into bright sunlight, how it takes a moment for our eyes to adjust. And if it's dim, then they open up again. This takes a little bit longer You'll have noticed if you've come out of a bright place into a dark room at night, it takes a bit of time for your pupils to dilate, we say. They open up, these circular muscles relax, and the iris opens up, letting more light through, and you can see again. We've also got ways of correcting eyesight. A person whose eyes focus well will focus a point on the retina, but somebody who's short-sighted, things that are far away, the light rays are not coming from a point, they're coming in parallel, and they focus in front of the retina, making the light that hits here a little blurry. So we correct it by having a lens that is thinner in the middle and thicker on the outside, and it bends it slightly, focusing it on the back of the retina. If somebody is over 40, the chances are they're going to start needing reading glasses. They can focus on things far away where the light rays are coming in parallel, but things that are close up get focused behind the retina, so it's blurry over here. So what we do is we stick some reading glasses in front, and reading glasses are thicker in the middle, and they bend the light a little bit, and then the lens does the rest of the work until it's focused at the retina. And these, as I said, are called reading glasses. Well, that's the introduction so far. Be sure to carry on and watching the one on reflection, then refraction, and finally color.